guys, what's up? Today we're talking about the spectral theorem. We're going to talk about the real spectral theorem, we're going to talk about the complex spectral theorem, and we're going to explain what the heck a spectral theorem is. But first, we got to do a little bit more. So we're going to show you a technical result first. I'm going to show you this quick little fact. Seems kind of weird at first. It's not actually that weird. I'll explain the connection to things that you already know, and then we'll get on with actually getting to spectral theorems. So instead of just rambling about it, let me prove this little technical fact first, and then we can actually get to it. So here's the idea. You've got T, an operator on an inner product space V. This operator is self-adjoint, and you've got B and C, two real numbers, such that B squared is less than 4C. Then T squared plus BT plus CI is invertible. Let me prove this really quick. Okay. Here is the gist of it. There's only one part that's even remotely, that requires much thought at all. So here's all we'll do. We'll say suppose that, well, I won't even say norm V is not 0. I'll say suppose V is not equal to 0. Then, here's what we get. We'll take T squared plus BT plus CI. Okay, and I'm going to apply it to V. And then I'll put V in an inner product with it. Okay. Now I'll just expand things out, and I'll get the inner product of T squared V, V, plus B, inner product of TV with V, and then finally plus C, inner product of V with V. That is, I just expanded this out along the first argument. Okay, this is not hopefully too terrible yet. All I'm going to do now is I'm going to flip some stuff using self-adjointness. So I can take one of these T's and apply it to the second part here. That is, I can take this and I can star it, right? Make it the adjoint. But since T is self-adjoint, this is just... Here, one second. Let me write the rest of this line out before I keep talking. There we go. Since T is self-adjoint, T star is just T. So this just turns into TV, TV. The rest of it be TVV plus C, inner product of V with itself. Okay, now some of these look like things we know. For example, the first one is the norm of TV squared. This piece right here, B, inner product of TV with V, is the part we'll have to concentrate on. And the last little bit right there, I get C times the norm of V squared. Okay, now Cauchy-Schwarz, if you remember, says the following. What does Cauchy-Schwarz say? Well, it says that the absolute value, or magnitude modulus of TV, I should even be easier here for Cauchy-Schwarz. Ugh, I can't write. Inner product of UV in modulus less than or equal to norm U, norm V. Okay, so if I put a minus on there, then I would flip this inequality, right? Agree with that? Okay, cool. So here's the claim I'm going to make. I'm going to say TV, norm squared, just keep that piece right there. I'm going to keep this C, norm V squared piece. And then what I'm going to say right here is that the line above is greater than or equal to, and I'm going to subtract off modulus of B, modulus of TV inner product with V. That is, if this bit here, B inner product of TV with V, is negative, this whole thing's negative, then this is in fact equal just by putting a minus sign, right? It's like saying if X is negative, then X is equal to minus the absolute value of X, right? So this is the same business, right? Except now I am just accounting for the case where it could be positive or negative. If it's positive, then this part's bigger for sure. If it's negative, then it's equal. Okay, but this sets me up to use Cauchy-Schwarz here to say that this is bigger than or equal to the norm of TV squared minus the modulus of B, norm TV, norm V, plus c norm v squared. But now this looks pretty much like some quadratics. Let's do a little bit of completing the square. Would you agree that this is equal to, and I'll just write it out really quick, norm tv minus modulus of b norm v over 2 squared plus c minus b squared over 4 norm v squared? Hopefully we agree with this. After all, if we go through it, we'll get a tv squared. Then I'll get two of these guys, so we'll get a b norm v times tv, and then I'll get another minus b norm v times tv, over, and both of them are over 2, and so when I add them together, I'll get back this middle term. And then with this last term, I'll get a b norm v squared over 4, right? And so this minus b squared over modulus b squared norm v squared over 4, and this minus b squared over 4 norm v squared cancel each other out, and I just get a cv squared left over, right? So if you don't believe it, just do the expansion. Simple algebra, nothing terrible. Multiplying out a quadratic, right? Okay, this is completing the square if you recall that technique from back in the day. And notice this is greater than 0. That is, if I want to do one more piece, this is certainly greater than or equal to, since this part is strictly non-negative, it's something squared, the smallest it could be is 0. This is definitely bigger than c minus b squared over 4 norm v squared, which is certainly bigger than 0, since, what did we assume? B squared is less than 4c. i.e., this says that if I just expand things out, c, or all right, 4c minus b squared is greater than 0. So 0 is less than c minus b squared over 4. Just taking a 4 out of that, yeah? Okay, cool. Multiplying both sides by 1/4, yeah? Okay, so this is bigger than 0. This is not equal to 0. Okay, so it's bigger than 0. Okay, so just going back to what we started with, t squared plus bt plus ci is non-zero if you apply it to v, if v is not 0. Hence, it is injective and thus invertible. Since it's an operator, it's a linear map between vector spaces of the same dimension. Wait, that's what we wanted to prove, that this thing here is invertible. All right, sweet. So this technical detail out of the way that says, look, for self-adjoint operators, certain quadratics of those self-adjoint operators are invertible. All right, seems silly, seems like a what the heck kind of detail is this? We'll use this in a moment. Let's keep it going. Let's start talking about the spectral theorem. Okay, here we go. Here's the build-up. This is the big piece that will let us get to the spectral theorem. So, first off, what we're going to show is that for self-adjoint operators, the minimal polynomial is of a really nice form. In fact, it's of a form that we kind of keep seeing, like when we talked about upper triangularity, diagonalizability, and so on. Diagonalizability by orthonormal bases, all these other things. This keeps coming up. We'll tie it all together, and you'll see why we care about self-adjoint and normal operators. They might seem sort of unmotivated why we've been talking about this, but when you finally see it in the spectral theorem, which is the next thing we'll prove right after this, you'll go, oh, That's why they're special. So let's see it. All right. What we're going to say is, hey, you got a self-adjoint operator on an inner product space V. Then our claim is that the minimal polynomial of this guy is factors completely into terms z minus lambda 1 through z minus lambda m for some lambda 1 through lambda m in the reals. Okay, notice we haven't even picked V to be a real vector space. So, first, notice, if our field is the complex numbers, then the zeros of the minimal polynomial of t are the eigenvalues of t, all of which are real. As we proved last time. So for self-adjoint operators, we showed, hey, look, eigenvalues are real. All right. So since polynomials factor completely over C, and since the zeros, so say since the polynomials factor completely over C, over the complex numbers, and since the zeros of the minimal polynomial are the eigenvalues of t and all of these are real, I'll say the minimal polynomial of t is of the desired form. Okay, so it has the desired form, where the lambdas are now the eigenvalues of t. Okay. Now, if the field is the reals, then we're going to have to do some more work. So if the field is the reals, we can't use we can't say that, hey, the minimal polynomial factors completely. We don't get that. So here's the business of it. Notice what we're going to do is use the fact that the minimal polynomial might not factor completely into terms like z minus lambda 1 and so on, but it will factor into some number of terms that look like this, and then some number of quadratic terms. Some number of quadratic terms that don't factor nicely into z minus lambda times z minus lambda, another lambda, for real lambdas. So that is, the min polynomial of t is of the form, let me write it, z minus lambda 1 through dot 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 all the way through z minus lambda m, and then z squared plus b1z plus c1, and dot 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 all the way down through z squared plus b, let's say n z plus cn, for some lambda 1 through lambda m in the reals, and b1 c1 through dot 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 all the way down through bn cn in the reals, such that now what we're trying to say is that you can't factor any of these quadratic terms any further. What is the condition that guarantees that? bk squared is less than 4ck. Since the roots of z squared plus bk z plus ck are z equals negative bk plus or minus square root of bk squared minus 4a, the first term is 1, times ck then, all over 2a, right? But a is once again 1. which is real, notice, unless this is less than 0, i.e. bk squared is less than 4ck. Okay, so the idea is that, hey, the minimal polynomial can be factored into some number of, degree 1 terms, monic polynomials of degree 1, and then some number of monic quadratics. Okay, and those monic quadratics can always be taken so that they don't factor down into monic linear terms, degree 1 terms. Does that make some sense? Because if you could factor one of these ones down, you might as well just do it and have more of the, make m bigger here, right? So we're saying that, hey, for some m, you've got as many terms as you can get of this form, and everything else can't factor. But now notice, this says, just write it out, t minus lambda 1 I through dot 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 all the way t minus lambda m I times t squared plus b1 t plus c1 I dot 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 all the way down through t squared plus bn t plus cn I is the 0 operator. And since t squared plus bn t plus cn I is invertible, we get, and I should say here parenthetically, if there are any such quadratic terms, that t minus lambda 1 I dot 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 all the way down through t minus lambda m I t squared plus b1 t plus c1 I dot 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 all the way down to t squared plus b n minus 1 t plus c n minus 1 I is also 0. Oh, ooh, this looks bad. Why? This would contradict the minimality of the degree of the minimal polynomial. Okay, so check it out. Since this last term here, and in fact all of these quadratic terms are invertible, you can always, if there are any quadratic terms, multiply by the inverse on both sides and get a polynomial of lower degree that also zeroes out t. It's also monic. Oh man. So that would contradict the minimality of the degree of the minimal polynomial, since the minimal polynomial is the unique monic polynomial of lowest degree that zeroes out t. Hence, there must be no quadratic terms, and the minimal polynomial must be of the form z minus lambda 1 dot 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 all the way down through z minus lambda m for some lambda 1 through lambda m in the reals. Oh, wait. That's what we wanted to show. Nice. So, when you've got a self-adjoint operator on an inner product space, either real or complex, its minimal polynomial factors completely into degree 1 terms. Man, that's nice. Why is that nice? Let's check it out. I'll show you the spectral theorem. You'll see it. You'll go, oh, that's kind of cool. Let's get into it. All right, you ready? Here's the real spectral theorem. Maybe I'm hyping it up too much. I like it. I think it's cool. Self-adjointness by itself is like, okay, that's kind of cool, but like, why would I care? Here's why. Here's why the self-adjoint operators are special. So in the case that the field is real, hence the real part of the real spectral theorem, and T is an operator on V, a real inner product space, the following are equivalent. T is self-adjoint. T is a diagonal matrix with respect to some orthonormal basis of V, and V has an orthonormal basis consisting of eigenvectors of T. In fact, what this says is that, so self-adjoint is the same as diagonalizable by an orthonormal basis of eigenvectors. That is, it's the nicest possible type of map. So, if you want to say, hey, when can I make my matrix diagonal? Like the simplest kind of matrix possible, the easiest possible type of operator, something that just acts like multiplication on basis elements. Well, when can I do this with respect to the nicest possible type of basis? That is a basis that is orthonormal and all eigenvectors for my mapping. The answer is when it's self-adjoint. So, the nicest possible types of operators are the self-adjoint ones. Self-adjointness is easy to check. It is as easy as taking a transpose, right? Remember that the matrix of the transpose is the the matrix of the adjoint is the adjoint matrix of the original operator. So that is the conjugate transpose of the operator's matrix. And in the case that we're in the reals, it's just the transpose. So it's easy to tell if something is self-adjoint. And if it is, look what you get. You get a diagonal matrix with respect to an orthonormal basis of eigenvectors, like the nicest possible type of operator. What like a powerful result you get for almost nothing. Just take a matrix, bada boom, transpose it. Easy, easiest check possible. That's the only time that you'll ever get a diagonalizable matrix with respect to an orthonormal basis of eigenvectors in a real inner product space. The only time it happens is when the matrix of your operator is equal to the transpose of the matrix of your operator. Oh, that's super cool. Such an easy thing to check. Let's prove this. It's actually nowhere near as hard as it seems. So, none of these proofs are going to be particularly technical. So, let's start out by supposing that A is true. Then, T has an upper triangular matrix with respect to an orthonormal basis of V since its minimal polynomial is of the form that we just proved in the last result. For some lambda 1 through lambda m in the reals. This is, if you don't recall, this is an old result we proved in chapter 6. With regard to this basis, the matrix of T is upper triangular, and since T is self-adjoint, we get the matrix of T is certainly equal to the matrix of T's adjoint, since the adjoint is equal to T, But this is just the matrix of T's transpose. Oh, when is an upper triangular matrix equal to its transpose? Well, just think about this. So that's lower triangular, while the matrix of T is upper triangular. So MT must be diagonal. That is, the only type of matrix that is simultaneously upper and lower triangular is a diagonal one. Ooh. Therefore, A implies B. B says that T is a diagonal matrix with respect to some orthonormal basis of V. All we needed to get was the fact that T has an upper triangular matrix with respect to an orthonormal basis of V. And then, because it is self-adjoint, we get that this matrix is in fact diagonal, just using the fact that the matrix of the adjoint is the transpose of the original matrix in the real case. Okay, so you've got A implies B. Now, suppose B holds. Then, the matrix of T transpose with respect to the basis from B such that we have a diagonal matrix. Okay, well this is equal to the matrix of T's adjoint, right? But notice this is still just equal to the matrix of T, since MT equals MT transpose. That is, we're assuming that the matrix of T here is diagonal with respect to some orthonormal basis. Hence, T equals T star, and B implies A. Oh, okay, so A and B are equivalent. That C and B are equivalent was shown in chapter 5. If you recall this, i.e., going back up, diagonalizability was the same as there being a basis of eigenvectors, right? So if we're diagonalized by an orthonormal basis, well then that basis is all eigenvectors. Just all you have to do is use the definition of what the matrix of an operator with respect to some basis is. It tells you how to write the image of a basis element as a linear combination of the basis elements. If that's diagonal, it means that all those basis elements are eigenvectors, i.e., diagonalizability is equivalent to the existence of a basis of eigenvectors of T. I should simply say diagonalizability of T is equivalent to the existence of a basis for V of eigenvectors of T. Okay, cool. So we're done. We've shown that C and B are equivalent, and we've shown that A and B are equivalent. So A and C are also equivalent. Bada boom. Easy. Cool. The real spectral theorem, not actually that bad. Basically, it says that the reason why you would care about self-adjointness is that, one, an easy to check thing, the adjoint of an operator is remarkably easy to, well, maybe not like easy to compute, but with respect to taking the matrix of something, it's remarkably easy to do. It's just a transpose. Okay. So adjointness, easy to check. It is equivalent to the nicest kind of possible property that an operator could have. This is easily one of the single most useful results in the study of operators. So we will revisit it. It'll come back, and you will probably see it in other places because, oh my goodness, it does a lot. It does a lot of heavy lifting. So that's the real spectral theorem. What about the complex spectral theorem? Let's get into it. Okay, the complex spectral theorem. Basically the exact same as the real spectral theorem, one tiny difference. Instead of self-adjoint, what we're going to do is in the complex case, we're going to assume that T, our operator, is normal, and we're going to say the following things are equivalent. Or we're going to take our operator, we're going to say the following things are equivalent. That T is normal instead of self-adjoint, and then the rest of the claims are exactly the same. T is a diagonal matrix with respect to some orthonormal basis of V, and then that V has an orthonormal basis consisting of eigenvectors of T. All of those things are the same. Okay, let's do the proof. This one is not too bad. I mean, compared to the buildup we had to do in the real case, that is like this like technical fact about quadratic operators of a self-adjoint operator, we don't need any of that silliness. So here, let's start with A. Suppose A, by Schur's theorem, from chapter 6, this is like the last result really there, there is an orthonormal basis of V, E1 through En, let's call it, such that the matrix of T is upper triangular with respect to this basis. Let the matrix of T be written as, well, I'll take A11, and then all the way through the diagonals, I'll get A and N, and then going across, I'll go across through A1N and down, and everything else is zeros. Okay, that's an upper triangular matrix. Cool. Then, notice the following. What does the columns of a matrix tell you? Well, the columns of a matrix tell you how to write the image of the corresponding basis vector as a linear combination of the other basis vectors. So this says that T, E1, is equal to A11 E1, and then the rest of it's all zeros. So the norm of TE1 squared is equal to the modulus of A11 squared, and check this out. Since the matrix of T, or I should say, since the matrix of T star is equal to the matrix of T transpose, so I should be careful here. I should say transpose, conjugate transpose. So I'll just write the matrix of T with a little star right there. Where the second star denotes the conjugate transpose. What we get is that T star E1 is equal to, now flipping it, we'll get A11 bar E1 plus dot 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 all the way down through A1N bar En. Oh, so you transposed it, you conjugated it, and now we have a way to write it. Okay, easy enough. So, since norm TV equals norm T star V, when T is normal, remember this fact from last time, that is, normal operators are those whose the norm of their image is the same as the norm of the image of their adjoint. We prove that that fact happens. we get norm TE1 squared. Well, this is just equal to the modulus of A1, 1 squared. And this is equal to T E1, or T star E1 in norm squared, which is equal to the modulus of A1, 1 squared plus dot 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 all the way down through A1n in modulus squared, since this is, after all, an orthonormal basis. Okay, very cool. Hence, just subtracting, we get a 1, 2 through dot 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 A1n. These guys are all 0. Repeating this process for E2 through En yields that the off-diagonal entries of MT are all 0. Hence, it is diagonal. Oh, man. And A implies B. Oh, that's cool. Okay, so remember, A said that T was normal. B says that T has a diagonal matrix with respect to some orthonormal basis of V. Okay, so kind of like the first one, kind of like the real case, we went and said, hey, look, we can get the matrix to be upper triangular with respect to some orthonormal basis. And then, kind of like the real case, we went and showed that this means that the matrix actually has to be diagonal. We couldn't just do the trick where we transposed it, because we also have to conjugate here, but just using some nice facts about normal operators, i.e. that they preserve norms, right, that TV is equal to T adjoint V in norm, at least, we were able to get this claim of diagonality. Now, let's do B. Let's show that B implies A. Then, the case of C and B's equivalence will be pretty much the same as before. So, now, suppose B holds. Okay. Then, T and T star both have diagonal matrices with regard to some orthonormal basis of V. In fact, with regard to the same orthonormal basis of V. Why is this true? Well, we're supposing B, which says that T has a diagonal matrix with respect to some orthonormal basis of V. What is the matrix of T's adjoint, T star, right there, right? The matrix of that is the conjugate transpose of the matrix of T. Take a diagonal matrix, transpose it, still diagonal. Conjugate all its entries, still diagonal. Okay, cool. So, T and T star are simultaneously diagonalized by an orthonormal basis. Okay, cool. Hence, since any two diagonal matrices commute, the matrix of T star is equal to, well, it's the matrix of T, matrix of T star, but they're both diagonal, so this is the matrix of T star times the matrix of T, and that's the matrix of T star T. Therefore, T star is equal to T star T, and T commutes with its adjoint. That is, T is normal. That's what it means to be normal, that you commute with your adjoint. So, B implies A. Okay, we've got A implies B, we've got B implies A. C and B's equivalence is the same as in the real case, which, if you'll recall, all we had to do was say, hey, look, we did this in chapter 5. That is, diagonalizability of an operator is the same as the existence of a basis for V of eigenvectors of that operator. And so our ability to diagonalize T with respect to an orthonormal basis, in fact, tells us that that basis is orthonormal and only has eigenvectors of T. Okay, super cool. We got the complex spectral theorem down. This is wild. This is neat. So, normality, not terribly hard to check either. Normality just says, hey, T and T's adjoint, they both have to, T and T adjoint have to commute, which means that if I take their matrices, then those matrices have to commute. So, just do that. Take the matrix of T with respect to some basis, then take the conjugate transpose of that matrix. All right. Does that new matrix you got commute with the original matrix you had? That is, does the matrix commute with its conjugate transpose? If it does, bada boom, you've just tested for normality and you've confirmed it, so you can conclude that there is an orthonormal basis consisting only of eigenvectors of T that diagonalizes T. Oof, that is nice. That is a powerful result, and it is probably one of the most useful results, like I said in the real case, in all of the study of operators. It will come back up, not just in this class, but if you take other, like physics and stuff, it'll come up there. It is a powerful result with far-reaching implications that we will begin to explore in the weeks to come. But for now, let's call it quits. We'll see you next time.